Hey, chemistry, coming up to our second half of our chapter, first of two videos and breaking up, actually, second half of chapter 2. I am adding a section from 6.1 after this section, but we're going to start with elements and compounds. Big question, how are elements and compounds different? Let's get started. There we go. If I was smart, I'd go ahead and roll my icon up here. Here we go. Substances can be classified them as elements or compounds. We just got done talking about the two different types of mixtures, but we can divide up our matter as in mixtures, things that are physically combined, into substances which are chemically combined. An element is the simplest form of matter, has a unique set of properties. Oxygen and hydrogen, two of more than 100 known elements. And this is what we deal with a lot. Compounds, a little bit different. Compound as a substance contains two or more elements chemically combined in a fixed proportion. As in, water will always have one oxygen, two hydrogens. Ammonia will always have one nitrogen, three hydrogens. And then you'll, excuse me, once we get into chapter 7 and 9, we talk about binary compounds. That's the kind of compound that consists of two different elements. And these aren't just mixed together, these are chemically combined. In this case with sucrose, carbon, oxygen, and hydrogen are chemically combined. If you ever come up on one of these notations, this is something for organic chemistry. Every bend of this little hexagon stands for a carbon. Of course, this one in particular is bonded to another carbon, an oxygen, and still another carbon. Every sample of sucrose, there's always twice as many hydrogen particles as oxygen particles, and it's always going to be the same makeup. That proportion of hydrogen particles is fixed in sucrose. If it's going to be sucrose, it's got to have so many hydrogens, so many oxygens, so many carbons. There is a key difference between elements and compounds. Compounds can be broken down into simpler substances, not by physical means, not by filtration or chromatography, but by chemical means. But elements cannot, not by ordinary circumstances. You might think about splitting the atom and talking about nuclear chemistry. We haven't got there yet. Just something you want to think of as just like under normal circumstances. We could break down compounds by running them through a chemical reaction, but elements, we can't do that. Physical methods, like what we've been talking about, distillation, which involves evaporating water. You can't use that to break a compound down in simpler substances. Boil liquid water, you get water vapor. It does not do anything to the H2O itself. If we wanted to separate hydrogen and oxygen, we'd have to perform what's called electrolysis. We'd have to actually, instead of applying heat, we'd have to apply electrical charge and get some gas collectors, because we have to apply a lot more energy than we get from that burner. Okay, you dissolve a sugar cube in water, it's still considered sucrose in water. This doesn't break down the sugar cube. This doesn't break the sucrose into oxygen, carbon, and hydrogen. This is a physical thing. This is making a solution, a sugar water solution. That doesn't mean you can't break down sucrose or water into simpler substances. But if you want to do that, you have to go through a chemical change. This right here is a physical change. This is making a solution. This is creating. Well, if you mix it all up together nicely, you get a homogeneous mixture. But let's say we want to break down a compound. We have to send it through a chemical change. A chemical change is something that produces matter with a different composition than what you started out with. Burning wood, rotting fruit, different things like using a battery, whether it's in your car or your phone, cooking an egg, exploding fireworks, sour milk, even digestion is happening in your body. Photosynthesis. Lots of chemical changes happening around us. Heating is one of the processes used to break down compounds into simpler substances. We think about boiling water to get it to 100 degrees Celsius. And a distillation, that would be a physical separation. In this case, we're heating sucrose. That layer of sugar is heated until it's going to break down into solid carbon and water vapor. It's probably going to smell pretty nice as we're caramelizing it. And then all you're going to have is just a whole bunch of carbon and water vapor. That's not going to be something you want to put in your coffee or on your cornflakes. What have you got? Now you've got something totally different from the sucrose that you started out with. Can the substances that are produced when sugar is broken down when heated also be broken down? Not ordinarily. The carbon, there's no chemical process that's going to break carbon down into simpler substances, because with that icky soot there you get, carbon's an element. We'd have to go through something really extraordinary. And again, the water vapor, if you want to break it down, you're going to have to condense it back into liquid and run an electric charge through it. So in this case, elemental carbon, you can't break it down. And you definitely can't. Well, you can't break anything down you can't break carbon down by even filtering. Not anything physical, not anything chemical. You'd have to go into something in nuclear chemistry. When electrical current passes through water, it's broken down. The water gets broken down into oxygen and hydrogen gas. That's called the electrolysis of water. And we have to force it to happen. Hydrogen and oxygen naturally want to combine to form water. But as far as making them do that, you've got to apply a big charge. And here's the reaction happening in the pan. Sugar getting heated down. Those carbons, oxygens, hydrogens, breaking and rearranging bonds to where you just get simple carbon by itself, and then the hydrogen, oxygen turns into water. In general, something to remember, properties of compounds that you get at the end of a reaction are different from the component elements. Sugar, like you start out with this reaction, sugar is sweet tasting. You try to eat carbon, if you're ever accidentally eating burnt toast, it's not number one on my top 10 list. You get this icky, tasteless black solid that's really not good for much. When we're talking about the formation of water, hydrogen burns in the presence of oxygen. It is explosive, it's colorless. Oxygen is also colorless where it's burning. But then when they get together, they form water, a liquid that can stop materials from burning. Two explosive gases forming a liquid. What you get out of a reaction, the properties of what you start out with are always going to be different from what you end up with. When sodium and chlorine combine to form sodium chloride, you get a change in composition, a change in properties. Sodium is a soft gray metal that you have to keep under oil, because if it reacts with water, it's going to react explosively. Chlorine is a pale gas. It's yellow and it's poisonous. So both of those elementally can hurt you. But when you react them together, you get sodium chloride, commonly known as table salt, a white solid. In moderate amounts, your body needs salt, but just not too much. You don't want to overdo it with salty snacks. But again, you see, here you have something, you got a white solid that your body needs in moderate doses. It comes from a metal that explodes when it gets exposed to water, and from a poisonous gas. You get something you can consume. Go figure. So how to distinguish substances and mixtures. We've been talking about that the last few days. Deciding whether a sample matter is a substance or mixture, just looking at it based on appearances, it's pretty difficult. Homogeneous mixtures and substances both appear to contain only one kind of matter, because homogeneous mixtures only contain one phase. Everything looks the same. You had sugar water sitting next to just a regular distilled water, it looked the same. Sometimes you can decide by considering whether there's more than one version of the material in question. Go to the grocery store, you can buy regular cow's milk and whole milk, low fat, no fat. You can get light cream or heavy cream if you're going to cook with it, if you're going to whip it into like meringue or frosting or something. From this information, you can kind of figure out that milk and cream are mixtures, because what you've got is a different percentage of fats. You might make the inference that the mixtures differ in the amount of fat that they contain. And again, another example of more than one version of the material, most gas stations offer at least 2 blends of gasoline, 87 and used to super super high test being 93. But the thing is, the blends have different octane ratings. Octane, it's a, let's see, it's a chain that's got 8 carbons, and gasoline engines burn it, but we have different percentages and different ratings. The lowest rating is considered regular. The highest rating, usually, again, 93. You've got kind of a super higher, maybe more pure blend. So you figure there's different versions of gasoline that must be a mixture. And of course, it's going to cost different per gallon. Something handy to think about. If the composition of the material is fixed, as in, if you only have one version of it, you can call that a substance. You only have one version of oxygen gas, of chlorine, one version of water. You want to say it's substance. Again, my rule of thumb is if I can find it on the periodic table, like an element, or if I can make it up with something that's on the periodic table, like a compound, that's going to be on our substance side. These things can be separated chemically. On the other hand, just a little review of, checking for time here, just a little review of mixtures. Mixtures have variable compositions. They're not set in stone like substances. And again, homogeneous mixtures, also known as solutions, heterogeneous mixtures, which look like they have distinct phases. All right, that's a part of this section. I'll catch you on the flip side for part B to finish this off. Bye.